In this video, we're going to calculate the necessary wavelength required of a photon to excite an electron from a lower energy state to a higher energy state. And so the excitation that we're going to be looking at is the excitation of an electron within a hydrogen atom from the n equals 1 state up to the n equals 5 state. So to do this calculation, the first thing we will do is utilize the Rydberg equation and generate a modified version that will calculate the energies of our initial shell and our final shell. And so the Rydberg equation is the energy of the shell is equal to the Rydberg constant, which is negative 2.178 times 10 to the negative 18 joules times z squared over n squared, where z is the atomic number of the atom and n is the shell of the electron or the orbital. And so the energy difference between the shells and the energy that's necessary to excite an electron from one shell to another can be calculated as follows. The Rydberg constant multiplied, and this is now going to be in parentheses, z squared over n final squared, where n final is the shell that the electron is going to end up at after the absorption, minus z squared over n initial squared, where n initial is the initial shell that the electron resided in. So if we plug in our values, where we have as n final 5 and n initial 1, we're going to get an energy difference of 2.091 times 10 to the negative 18 joules. And that's how much energy is necessary to excite an electron from the n equals 1 to the n equals 5 shell. To calculate what the wavelength of light necessary is to do this excitation, we'll use the equation lambda is equal to hc over E, where lambda is the wavelength, h is Planck's constant, and c is the speed of light. And so if we plug in our values, what we'll have is 6.626 times 10 to the negative 34 joules seconds times 3 times 10 to the 8th meters per second over 2.091 times 10 to the negative 18 joules. And so what we can see is that the joules will cancel out and the seconds will cancel out, and we'll end up only with a unit of meters. The wavelength of light necessary to do this excitation is equal to 9.506 times 10 to the negative 8 meters. Or if we were to just shorten it, it would be 95 nanometers. So to recap, what we did in this video is we calculated the necessary energy of a photon to do an excitation from a lower energy state to a higher energy state, and then calculate what that necessary wavelength is of that photon.